All right. Hello, everybody. Sorry for the brief technical issues that I was running into. Now it seems like everything's working. Let's get the lecture started. So this is our 14th lecture, and we are on the topic of offline reinforcement learning. So far, we've been talking about the off-policy evaluation problem. Today is the first lecture that we'll start to talk about offline RL in terms of offline policy learning and policy optimization. Okay, so we'll introduce what the uniform off-policy evaluation is and how to derive the first bound in uniform OPE. All right. First of all, what's the difference between offline policy evaluation and offline policy learning? So in offline policy evaluation, we consider a fixed target policy that's chosen independent of the data. And in off-policy learning, so typically what we want to do is to identify a new policy that is as good as possible. That maximizes the reward as much as possible. Suppose we start to run this new policy in the same environment again and again and again. Okay, and today we're going to take the approach of so-called uniform convergence in order to find nearly optimal policy. Okay, so we'll start up with a quick recap of the last lecture. In this lecture, we moved from offline policy evaluation from the contextual bandit setting to the reinforcement learning setting. We focus on the particular model on the finite horizon episodic Markov decision processes, and we use data that collected by running logging or behavior policy, which we call mu. And the goal is to evaluate the target policy. That is what we call pi. So notice that this mu and pi, they are all tuples of mu1, mu2, and mu h. Each one of them, mu t, is a mapping from the state space to a probability distribution on the T section space. And since this is finite horizon episodic MDP, the space doesn't even need to be the same at every time point. And in particular, even if the state's the same, we consider that the state space is the same. We consider each individual state to be specific to that time point. And then this goes similarly to the pi 1 to pi h. Okay, so these policies are still they are non-stationary since it depends on t, but they are still Markovian in the sense that they depend only on the state that you observe at that particular time point. And in the last lecture, we talked about many OPE estimators for the reinforcement learning problem, starting by extending the ideas of importance sampling from OPE to RL. So we talk about reweighting the entire trajectory using, and the importance weight happens to be the product of the importance weights of taking the same action in different time steps. And then we talk about a slight improvement of that called the per step importance sampling, which we'll talk about again today. And the doubly robust version of the importance sampling estimator, which we add a regression estimator to predict the future values at every time point. Okay, and we talk about this issue of so-called curse of horizon, which says that all these methods above, the trajectory-based IS, per step IS, and W robust, they suffer from exponential dependence on the horizon in the variance of those estimator, which essentially says that if you want to have an accurate estimate of a given target policy with these methods, you need to collect exponentially large, so e to the power of h number of trajectories in order to get to a constant error. So then we move on to talk about the idea of overcoming the curse of horizon by using an improvement of these importance sampling estimator by marginalizing and taking advantage of the marginalizing over the state and taking advantage of the multiple observations of the same state. Then it turns out to reduce this sample complexity from exponential in the time horizon to polynomial in time horizon. Okay, so that's a basic story that we went over in the last lecture. So in today's lecture, let's like look at these problems again, but this time let's consider the policy optimization problem, right? So in order to do that, let's set up the notation. So as a refresher, so all of us will be on the same page. So in the finite horizon episodic MDP, we have state space, action space, the transition kernel, expected reward function. So instead of the discounting parameter in the infinite horizon case, now we have now we have H, which is the fixed horizon, and then there's this initial distribution of the state, which we denote as D0. Okay, or yeah, maybe D1. Yeah. So these we consider the time varying transitions. So that this P is actually P1 to PH. So this is a state transition at time 1, transition in time H. So all of these are from state space, action space to a probability distribution on the next state. Okay, and similarly, like that goes for the reward. Okay, and then there is a Q function that's also indexed by time, and Q star function, VT, and V star function indexed by indexed by the particular time step. Okay, and the Bellman equations. So you have a finite. You have H of them, which tells you the recursive formula that goes from the last step all the way to the first step through the Bellman, the familiar Bellman backup. Okay, so the data that we collect in this problem is drawn from by running a behavior policy mu, and this gives us S1 A1 R1 for the first trajectory, for the ith trajectory, S2 A2 R2 to SH AH RH. So all these are random variables, and with a superscript I indicating the trajectory index. So the total number of n trajectories. And like I said, this is a logging policy. There's also this target policy. And we consider this to be conditional probability distributions. So we can talk about for any A and S and T, we can talk about the importance weight of the target policy taking action A at state S at time T, right? So we define this to be we define pi T and ATI STI over mu T ATI STI. So these are your observed variables to be rho T I. Okay, so this is per step importance weight. So moreover, we can define this to be a function of the state and action at time T, right? So this is a importance weight of this particular step for given state and action. Okay, so typically we assume that the target policy and logging policy are given. We are given function access to that, so we can evaluate these quantities by plugging in the different state action pairs. Okay, so that's the notations that we need. So the main challenge that we run into in using the importance sampling estimator, which is given by this is per step version of the importance sampling. So what this does is to reweight the probability distribution that gives rise to the same sequence of states and actions until time h, right? Until time h, and then you collect this reward, and then we can divide the probability of the probability distribution of getting to this point, and from the logging policy, and then multiply the probability distribution of all the random variables that leads to this point. And so this reweighting will give us an unbiased estimator of the performance of the target policy. And the issue really is in this product. So each individual importance weight can be something that's, say, even if it's something that's between 0 and 1, then the product of that could be as large as 2 to the power of h. So this can be, this is smaller than 0, larger than, it's not negative, but it could be as large as, say, max rho PSA to the power of to the power of h, right? So that leads to a possibly exponential blow up in the variance of this importance sampling estimate. We've constructed one particular example where you have several states, and one action takes you clockwise, the other action takes you counterclockwise. So in this case, you can have very different policies, but then they actually give you very similar state action visitation, right? So from this example, we see that this is actually a problem that in many cases we can solve, rather than it is like such a fundamental issue that applies to all algorithms out there. Okay, so the idea of addressing this that we discussed last time was to marginalize the importance weight by applying a recursive formula to make more efficient use of the data. So in particular, so the MIS estimator is an importance sampling style estimator. But the importance weight and the reward, they're all averaged over individual data points that leads to the same state. So in particular, this reward is by collecting all the states from all the past trajectories, and then takes the average of that with the importance weighting. So this is IS importance weighting to at only time t, right? So this only requires us to reweight using phi t STI ATI, using only these, and this quantity is very easy to handle. Yeah, I think I might actually have a slides about it. Yeah, so this one is easy to handle since this is under mu, right? So this is we have data that's collected by running this policy mu. So we basically take every time step and count the number of times that we've run into this state, and then that gives us an unbiased estimator of this quantity. So what's the only like challenging part of instantiating this MIS estimator is to come up with a valid estimator and a good estimator for the numerator, which tries to estimate the state action visitation according to the observed data, right? So the idea is the following: since under the original MDP, due to the Markovian property, and you guys have worked this out in homework 1. So this is a matrix vector multiplication. So you start with your initial state distribution, you apply the state transition. So this is P pi, and this is your initial state distribution at the time, say at time t, and this is state transition that gets you from t to t plus 1, and then if you follow policy pi, this is an S by S matrix. This is S by 1 state visitation measure at time t, and the transition matrix will take you to the next step, and then you'll get dt plus 1 pi, right? With this, the idea is that maybe we can somehow estimate the transition kernel, like using importance sampling, and then recursively apply our estimated transition kernel. So at the end of the day, we'll get a better estimate at every time step for this target policy pi. Right. So under this idea, we designed this importance weighting estimator for the transition kernel, which collects all the different times within the trajectory that you run into this particular state st minus 1, and then I'm enumerating all those cases when you're starting from here and then actually transition to the next state being some fixed value st. Right, and this importance weighting estimator, so this is IS for estimating the transition dynamics, and if we do that, actually only estimating the transition dynamics on the pi, right? Because we're not requiring us to visit every action for many times. Also, all we require is that we visit the same state for many times. So this can potentially work for cases when the action space is unbounded, right? So let's say that this action space is a continuous value between 0 and 1. So what this requires is that this mu and pi, they have a density ratio that's somewhat bounded for this estimator to have low variance. Okay, so that solves the problem of estimating d hat of pi. And by substituting this, then we get the MSS estimator, right? And we saw that the MIS estimator, it is handles infinite action space, and we work out its variance and and explain some ideas in deriving the variance bound for MIS. And we'll see that in the next slide. But the story went that the variance is actually a factor of h away from being optimal, right? So that motivated us to consider like a specialized version of the MIS estimator called the tabular MIS, where the only difference from the original MIS is how we construct these estimators in the first place. Okay, how we construct this and how we construct these. Okay, so the what are the differences? It turns out that we only have to change one thing in order to make the MIS into the tabular version and then gain the benefit of a smaller variance bound. And the idea is that like we've seen this from working out the expression in the tabular, I guess in the multi-arm bandy case. Right, so we've seen that the regression estimator actually has an importance weighting type interpretation by replacing the denominator of the importance weight from the actual propensity for the actual probability of taking the actions to the empirically observed probability of taking that action. Right, so what we can do is to change this numerator in the construction of this importance weighting estimator into mu hat. Right, so by changing this into the empirical estimator and then and then plugging the same formula, it gives us the tabular version of the Markov the marginalized importance sampling estimator. Okay, so what we got was that the mean square error for the MIS estimator obey this following expression, which looks complicated, but it captures the essence of captures the essence of the challenge of the problem. So specifically, let's first ignore the low order term. So as the number of trajectories gets larger, so this goes to 0 substantially faster than the leading term, and focus on the leading term. And we can see that the leading term depends on the importance weight. So this captures how different the logging policy and the target policies are. And similarly in the variance, so this captures the per time step, the importance weights, the discrepancy of the probability of taking the same action between the two, between the logging and the target policy. So both of these two require the logging policy to explore a little bit relative to the state and action distribution that's taken by the target policy. So everything like makes sense, and these are the standard value function, and this is immediate reward, and this is the reward that you see in the future, right? So everything makes sense. Like the MIC bound of the marginalized importance sampling estimator is what we expect it should be, and when we change it to the tabular setting, and this bound can be further improved. And the only difference is that now the variance, so this variance, notice that is conditioning on ST. And the only difference is that now we're also conditioning on the action. And this importance weight can be extracted outside this variance to be square of this quantity. Right, and this expectation will give you the state action pair under d mu st and mu t at, and those two cancels with one of these factors on the exponent, so you get this this pi square over mu style summation that we saw in the variance analysis of the contextual bandit setting as well. Okay, so the improvement from IMIS to TMIS is a Jensen's inequality in some sense. Is to further condition on something and then getting rid of the one part of the law of total variance. So if you expand this variance using law of total variance, you will get this. But in addition to this, you will also get something else. And that something else got eliminated when we consider the tabular version of MIS. Okay, so asymptotically, we made like several assumptions to simplify this expression. First of all, n is large. So when n is large, then we can we don't need to worry about these low order terms. So at least the low order term is on the same order as the leading term, then that's a threshold that we consider and to be sufficiently large. And the second assumption to third assumption to simplify this expression is to say that pi and mu, they are somewhat similar. So first of all, for any t s and d pi t of s over d pi mu of s is smaller than something like tau of s. Okay, so let's say that the importance weights are bounded, and thirdly, for any t, s, and a, pi t a given s and mu t a given s, so this is also bounded by some constant tau of a. Right, so these are constant that like very crudely captures the how different the two policies are. So if we have these bounds, then we can simplify the expression by replacing these quantities with the upper bound, tau s and tau a. And once we do that and change the measure to under pi, then we can show that this is smaller than 1 over n sum over t tau s tau a e under pi, and variance on the well, variance on the yes, variance still under mu, VST plus 1 plus RT given ST. And this quantity we can bound it by H square. So ultimately we get 1 over N. Yeah, there's also a summation over yeah, there's yeah, this is summation T from 1 to H, right? So you have H cube tau S and tau A, right? So that will be a simplified expression for the bound of IMS estimator. So it depends cubically in the horizon, and it's a polynomial dependence rather than exponential dependence. And in TMIS, let's work out the same algebra by applying these assumptions. So we can replace one of these. We can replace one factor of d pi over d mu by tau s. So this is smaller than tau s, and times the probability. And the second part is smaller than tau a, multiply with pi of a given s. Right, these two, if we group them together, they are probability distributions, and we're summing over the different state action pairs. So they gives us 1, and these are constant. Then we can extract it out, and then we're left with 1 over n tau s tau a, and then sum over h and the conditional variance of v under pi plus RH1 and SA, right, condition. And yeah, so it is so we can use a naive bound by replacing this conditional variance with just h square, which would recover, like together with this summation, which will recover the same h cube rate, right? But we can actually do something that's fancier, right? Since now that we have extracted everything that's outside, we can actually show that this part is altogether, it is a summation of h, potentially h square large individual element. The whole thing can be actually bounded by h square, right? So this is by this is by working out this variance decomposition, right? So this is something that we've seen last time. So under any given policy, right, and suppose we run this policy to collect the data. So this is on policy case. And the variance by first principle looks like the variance of summation of the reward. And since the reward is bounded, and each reward is bounded by 1, so we know that this quantity is bounded by h square. On the other hand, if we apply the Bellman equations, and if we apply the Bellman equation of the empirical Bellman equation of variance, then we can decompose this into the groups of 2 summations by repeatedly apply the law of total variance, right? So we can see that if we do this, then the first term, so this expectation of variance term summing over t from 1 to h, is exactly the quantity that we are looking at here. Okay, and in addition, the second part is larger than 0, right? So therefore, like, we know that this part, even though it is a summation of seemingly h square large numbers, cannot actually reach h cube. Instead, like, by using this simple argument, then we can show that this quantity from TMIS is actually smaller than h square. Yeah, this is something that I glossed over a little bit last time, but I hope this further explanation made this a lot clearer than what I did on Monday. Okay, to say it differently, so notice that we're dealing with the mean square error, right? We're dealing with the square error. So in terms of the error of TMIS, so if we consider the absolute error, the scale should be the square root of the error of the square error. So what we should get is proportional to just one factor of h over something like 1 over square root of 1 over square root of n. Okay, well, so since we're estimating a quantity that can be as large as h, right? So this is saying that there isn't any additional dependence on the horizon that comes into the picture. So essentially, we're getting we're getting something that matches the same result. So let's say that there are no dynamics at all, right? And it's only that in every time point you are running a separate multi-arm bandit problem, and in order to estimate that, in order to estimate that problem accurately, then you still need to incur an error that's this large. Like in this sense, we're not really losing anything in terms of the horizon dependence. Now, another interesting observation from this lemma is that if you take this marginal importance sampling approach by incorporating the Bellman equations, and you are even improving over the results that you can get with on-policy evaluation, right? So let's what does on-policy evaluation do, right? You take this policy, you actually run it. You run it n times, and then you are taking the average of the cumulative reward that you receive, right? So this is an empirical mean estimator. In many cases, you would think that this is the best that you can get. But in this case, it's not really the case because you can actually get rid of the variance that's present in the on-policy evaluation part from the variance of expectation factor. Okay, so when there are structures, like taking those structures into account when designing algorithm will sometimes lead to some savings. Okay, and then what's the intuition behind MIS and TMS or overcoming the curse of horizon? So if we take a step back and look at it again, it is really that these estimators and these algorithms, they are relying more strongly on the model assumption that the data are coming from a Markov decision processes, and they are exploiting the fact that MDPs are Markovian. On the other hand, the standard IS and doubly robust and others, so they work regardless of whether the Markovian properties are true. So suppose you have a POM-DP where your actions is only where your actions depends on the observations that you see in the past, then you can apply the importance sampling and doubly robust estimator there, and you will get an unbiased estimator regardless. Right, so they are not making use of the fact that the state that you observe is actually the state, and so in practice, so sometimes even though there are exponential dependence on the horizon, like using the importance sampling and doubly robust methods, so they could give you results that are more reliable to model misspecification. On the other hand, they have exponential variance, so typically you require a lot of samples in order to accurately estimate the value of the target policy. Okay, so another interesting observations that we made last time was that the tabular version of MIS is actually just equivalent to a model-based approach. Okay, so how do we see that? And what is a model-based approach in the first place? So the model-based approach is simply estimate the empirical Markov decision process with SA and replace P with P hat, and replace R with R hat, replace the initial state distribution with our empirical estimate of the initial state distribution. And all of these can be, since this is a finite state and action case, all of these can be just replaced by the plugin estimator, which takes all those cases that you observe and estimate this empirical probability distribution. And for this expected reward, then let's just take all the state action that you've seen and then pool average over the resulting reward that you take the same stated action, right? So by doing that, we can construct a approximate model of the world, so the approximate MDP, and then we can do any kind of planning that we want. We can do policy evaluation. We can simply roll out with a simulator that actually runs these with this p hat and r hat. Yeah, we can do whatever we want by online evaluation of the target policy on this approximate MDP. Okay, so this turns out to be the same as MIS, and the reason is the reason is the following. Like suppose we we've used this trick again and again in this quarter. So when we're summing over the different time steps, and when these are random variable, we can group those cases when these random variables take the same value, right? So we can introduce this summation over state instead, and then this decompose. Then we get rid of this summation over n, and then we can when we are using TMIS, since these are the just empirical estimator of the state visitation distribution on the mu, and that cancels out with the number of times that each state is visited, right? So in this way, like we do not need to know what the login policy are when implementing the tabular version of MIS. Okay, so why is this equivalent to the model-based approach? And that's because by our recursive call of recursive estimator of this, so this is the p hat t minus 1 under pi and dt minus 1 mu s prime. Yeah, so this is a matrix vector multiplication, and these are actually constructed using the empirical frequency, right? So in TMIS, based on the equivalence of the regression estimator in multi-arm bandits, so we've seen that if we do everything in the tabular way, and this becomes just a plugin estimator, right? So with this recursive construction, then we know that these state action visitation are the exact state action visitation according to the approximate MDP, and these rewards are exactly the same as the rewards that's coming from the empirical estimated rewards. Therefore, this is simply by the definition of the model-based approach, and this gives rise to the model-based estimator. Okay, so in today's lecture, the first thing that I'm going to tell you is it's another algorithm that appears to be very different, called fitted queue iteration. So this is a classical algorithm that's used in that's used in reinforcement learning for data efficient way of doing batch reinforcement learning or offline reinforcement learning with a given data set. Yeah, so we'll see the connection of the fitted queue iterations to the tabular version of MIS and the model-based estimator in the next few slides. Yeah, and then once we are over that, we'll start to talk about the uniform convergence of OPE in RL, and I'll set up the problem, and maybe prove a simple version of the uniform convergence bound, and then I think that will be the content of today's lecture. And we'll resume and talk about more offline policy learning and policy optimization in the next lecture. All right, so fitted queue iterations. So we'll start from so these fitted queue iterations, or FQI, they are like policy optimization methods. At least in the instances when they were first proposed. So the idea is actually very simple. So you guys still remember the Bellman optimality equation, right? So the Bellman optimality equation says that if you have a Q star function, and the Q star is a fixed point of this Bellman Bellman operator. So Q SA is equal to the transition into the next state S and A, and then the V the V star function, right? And you can view this matrix as a SA by S matrix. So this is an SA by S matrix. So this is the Bellman optimality equation, and you can write it with only Q by you can write it with only Q by replacing this with max max A prime of Q star of S and A prime, S prime and A prime, S prime, sum over S prime. Okay, if we use the summation notation, so this is what it is, and then we could also use the matrix notation or the notations that I used just now. So this is the Bellman optimality equation, right? So when you are discounting the future rewards in the infinite horizon case, you introduce this gamma, right? So you introduce this gamma to the second term here. And Bellman operator takes a function and then apply this Bellman optimality updates, right? So we've seen that if you repeatedly apply the Bellman operator, so that algorithm is called value iteration, and if you know the model, and that converges to the optimal Q star function for that Markov decision process. So now the thing is that how do we take advantage of this and come up with an algorithm that takes an offline transition data, or maybe offline transition data together with a random reward data. So your data set will be of the form of SAR and S prime, right? And indexed by I. So you have many copy of this, I from 1 to n. So in this case, like I'm glossing over the details and distinctions between episodic MDPs and the infinite horizon MDP, because they work initially on the infinite horizon MDP case. So in this case, once you have this offline data set, right? So you can check, you can try to fit a Q star function by searching from a particular function class to find the best approximation of the Q star function that's consistent with this Bellman equation update, with this Bellman optimality equation. Right, so what you can do is to solve the optimization problem that looks like the following. So let's not worry about how you actually solve this optimization problem, but you could you could do this iteratively by initializing from I guess what you ultimately want to solve is the following f s prime a minus ri minus gamma and max a prime, and you substitute the same f here and s I a I square. Yeah, I actually think that this is S prime, this is A prime. Okay. So this should be S prime, A prime, and this should be S. Yes. Yeah, sorry for the typo. Right, so this is what you want to minimize. So do you want to find the function within the function class that is, like, in terms of the least square distance, it is closest as close as possible to the to one that is consistent with the Bellman equation. Okay, that makes sense, right? So from optimization point of view, like, you want to find such a function that optimizes this objective function, that minimizes the least square error. And the proposed fitted Q iterations is to simplify this optimization problem, because even if f is linear in some, so even if f s is equal to some parameter inner product with some known Fisher mass SI AI, so even in this case, when you have a maximization inside the inside the square, and then it becomes like very difficult to solve this problem. So they propose this iterative algorithm that initialize from some S0, and then like iteratively plugging S0 into this, get F1, plugging F1 and get S2, and then each time you solve this problem becomes a simpler, like a least square optimization problem, right? So in every iteration you are solving like a linear regression problem to identify what the right theta is. Yeah, and sometimes, right, you add additional like regularization term with a theta square with some carefully chosen lambda parameter to make it more stable. Okay, so that's FQI. So I argue that this is like very general, and you can apply this to cases that's beyond the tabular setting. You can apply this with neural network if you take this F to be a deep neural network, and that's actually what people do all the time in deep RL literature when you do experience replay and other like batch RL style algorithm design tricks. Okay. So we can work out the same idea for the episodic case without actually without actually doing infinite many iterations until it converges. So in the finite horizon case, we can start with the last step and then solve basically we can solve this as H AHI minus R HI square, right? And there are no H plus 1 steps, right? So we know that this is the last step, and this is easy to solve. It's a least square optimization problem. We can find f of H. And once we have f of t, we can get ft minus 1 to be the arg mean of f. Now this is f s t minus 1 a t minus 1 minus r t minus 1 and then this time, so we will have this we'll have this remaining future reward term, but this is a constant. This is already fixed based on our knowledge of ft, right? So we can just substitute ft into here. Yeah, so maybe I should use h to avoid confusion. So h, suppose you are given f of h, then this is s hi. So this is the actual part that you transition to, and a prime square, right? So this is only an optimization over this f. So in the linear case, this is linear regression, and in the like neural function class case, these are something that in practice, like we know it is easy to optimize with stochastic gradient descent. Right. So now we have an infinite. So this is a valid algorithm for things that we haven't talked about in this class to find the optimal policy. Because once we have this sequence of f1 to fh, we can take the argmax of that. That gives me the greedy policy, and it's my best effort of trying to do offline policy optimization. But today let's talk about the OPE. So we can design a similar like fitted queue iterations for offline policy evaluation problem. So recall that the Bellman equation for a given policy pi, and we can write out this Bellman consistency equation that is a linear system of equation for Q. Okay, so far the right hand side is written as a function of h, but we can further rewrite it as a drawn by pi s prime and q h pi s prime and a prime given s prime and given s and A, right? So this is over the state transition. This is over the state transition, and this is over the policy, right? So once we do that, then we'll have a linear system of equation for the Q function itself, right? So we can use the same idea of fitted Q iterations to do policy evaluation, right? So we can what we can do is to again go from the very last step and solve the least square problem. So in this case, you don't really have this term, right? For h equals to h, this is 0. Above is equal to 0. For h smaller than h, then you can recursively get the previous qh of pi and then plug that into this fh plus 1. Take fh h plus 1 to be q hat of h plus 1 pi. Okay, so I hope it's clear that this is a valid optimization-based algorithm that tries to minimize the least square error. And you can solve this efficiently. Suppose this f has a linear function approximation. And if, like in the tabular case, it's like a special case of the linear case. And you're basically just getting the like some numbers for the corresponding like Q pi function for every state action pairs separately. Okay, so now maybe let's work out like what the optimal solution look like for the tabular case, right? So let's work out the optimal solution. So as a matter of fact, like this is a relatively simple optimization problem to solve, right? It's a quadratic optimization with the only thing that depends on here. And then we can simply take the gradient and then set it to 0, right? So and the parameters are shared according to the S and A, right? So let's do it. So first of all, FH of SHI, AHI is just the I guess in the tabular case is some well, so it's let's maybe do it this way. Let's call this theta to be in S and S by A, right? So this theta is a parameter of your Q function, and we know that this becomes the inner product of theta and indicator vector of SHI. AHI. So this indicator vector gives you the one hot representation in this vector SA, and it is one for the coordinates where you actually have this SHI, AHI, and in all other coordinates you have 0. Okay, so this is equal to theta SHI AHI. Right. So suppose we take the partial derivative with so take the partial derivative with theta SA for any for a given pair of S and A, right? Of this objective function, and what we get? We get sum over 2 times, right? We'll apply chain rule to do this, and for those SHI and AHI that are not really like the same as A, that we get 0, and for all the others where they are actually SA the same SA pairs, then we can do the following, right? So we will have first of all the residual, so it will be theta SA minus R H of I. Yeah, so maybe theta H. Theta is also indexed by H. Minus Yeah, these are things that we actually know, right? And fh plus 1 is also something that we know, right? These are coming from the previous iteration of what we get, right? And do we have anything else? So by the chain rule, so there are no multiplier in front of this parameter. So I guess what we get is just an indicator, right? What we get is this indicator vector. So when this is 0, then we get 0. When this is 1, then we get 1. So we have this indicator of S I AHI is equal to so now this is not a vector anymore, since we're taking the partial derivative. This is equal to SA, right? So what these two together like selects those coordinates that happens to be as the same as a pair. So we need to assign this to 0 in order to calculate what the theta SA. So theta SAH, this is equal to this is equal to the summation of I from 1 to n indicator SI H A I H is equal to SA. So this counts the number of times. Yeah, so this multiplied with the theta SA theta HSA. So number of times we see SA in the data, right? So you have that, and this minus the sum of RHI. So these are the rewards and the future future value. So I'll call this E on the pi FT H plus 1 S H plus 1 A prime, and these are random variables that we can average over things that we know. Plus, and we can group these two together with this indicator of SI AI is equal to SA pair. Right. So what do we get? So when we assign this to 0, what we are really getting is that the theta HSA becomes the empirical averages of these that we observe. So they will become the R hat H S A, right? So that's empirical average because I'm simply taking the 1 over that. And I'm simply dividing the data that we collect by the number of times that I have samples for, and for the second part, since by recursive applying this from the very backwards, so these are really our estimate of we had on the pi by rolling out the policy as and together this expectation is expectation over like these are expectations over the state transitions. So notice that when we average over the indicator of SH plus 1, then we are using the empirical transition. We're using the empirical transition here. So what is this ultimately? So this becomes identical to the model-based approach. So this becomes like exactly the same as running the value iteration as the estimated model, right? So running the Bellman backup with a fixed policy pi using an empirical estimated model. And what this is telling us is that in fitted Q iterations, although it is motivated very differently, it is actually identical to the same model-based estimator, and also identical to the tabular Markov tabular version of MIS. Yeah. Actually, so this is output from the fitted Q iteration. So once we get this all the way to the step 1, then we get this Q hat function, and then we can plug this in together with the estimated initial state distribution and your target policy, and we can plug this in, and that like gives us the first principle definition of the value of that policy with this particular initial distribution on the pi. Okay, so in conclusion, so there are like 3 different approaches that we've seen. One that's coming from the importance sampling perspective for the interest of like breaking the curse of horizon, and the second is coming from the complete model-based plugin. So let's just do the old trick of estimating the model and use a simulation lemma kind of result to justify this, and then the model-based approach by just directly simulating the estimated models, and we'll get some estimator. And the last one, so let's follow from optimization perspective and derive the sequence of Q function from backwards. And like notice that this in TMIS, the sequence of recursive estimator is the state action, it's a state visitation, so or the occupancy measure at each time t. And we can construct this by estimating the first one, and then recursively estimating the second one and the third one. So this goes from h from 1 to h. So the fitted Q iterations go from backwards. It starts from Q hat H, which is the easiest for you to do. And once you have that, you recursively estimate Q hat of H minus 1, and then give you Q hat of H minus 2, and all the way to Q1. So once you get Q1, then you can plug in this alternative formula for the value, and that gives you a value, right? So you can think about TMIS and the fitted Q iterations to be dual to each other, like according to the LP representation of the Markov decision processes problem. Okay, so it's not surprising at all that in tabular MDP that they're all equivalent. So as we generalize beyond the case with finite state and finite actions, these different variants provides different ways for us to look into which quantity does it make sense to use a neural network to approximate, right? So in the fitted Q learning, so we are approximating this Q function with a neural network. But alternatively, we can take the dual view and then approximate this state action visitations with a neural network. Right, so there are different variants of coming up with generalizations. They are all equivalent for the tabular case, but the different variants of doing functional approximation could have different implications and different performances, and some of them would work better than others in the practical like deep RL applications. Okay, so let's take a short break for 5 minutes, and as we resume, we'll talk about offline policy learning, and we'll talk about the uniform of policy evaluation. All right, see you guys at 2:15. And meanwhile, if you have questions and other stuffs, just please type them into the chat. All right. Welcome back to the lecture. Um, let's resume. Um, we'll move on to offline policy learning. And just now, what the last slide should tell you is that the model-based approach in offline reinforcement learning is in some sense somewhat fundamental, right? So in order to get efficient learning, in order to get to overcome the curse of horizon, it requires us to have some idea of what the model is. So computation efficiency on the other hand, and space efficiency on the other hand, it doesn't really matter whether you use like a model-free approach or the model-based approach. It doesn't matter how you design your algorithm. So ultimately, it will somehow like rely on like the structures are imposed by the Markov decision processes itself. So one way or another, you are taking advantage of the model assumptions. So so let me jump out a little bit and then talk about on a high level. So what these two problems are really solving, right? So we've been talking about OPE for quite a few lectures. So in its essence, it is a statistical estimation problem. So we are given IID samples from some distributions that's collected by running the logging or behavior policies. And then we want to estimate some like single value, like a univariate statistical quantity, right? So this quantity is indexed by a target policy pi. I see if that target policy pi is wrong. So this is a statistical estimation problem, and or just a causal inference problem that we want to replay since the data that we have collected by taking one set of actions and understand what's going to happen. Like suppose apply a different set of actions. So there are two cases where a causal inference problem can be solved. So in the first case, this is when you actually have a model of the world. Let's say that you have a causal probabilistic graphical model, and there are no missing data anywhere. You know the joint distribution. So in this case, you can once you have this model, then you can work with that model in any way you want, and then that corresponds to the realizable case, right? So when we know that the data is generated from a Markov decision process, then we can do off policy evaluation and evaluate another policy. In some sense, like more efficient than any other approach would do, thanks to the principle of maximum likelihood estimation. And well, so there so we've been focusing on the second performance metric, that is the mean square error of this estimator, and the difference from the standard like statistical estimation problem. Say like I'm telling you that you got samples from a coin tosses, and you want to estimate that parameter p of this biased coin, or suppose you have samples from a multivariate normal distribution, and you're asked to estimate the mean and the covariance matrix of these sequence of random variables, right? So comparing to those problems, the OPE has nuisance parameters, right? So the number of parameters that describe the model, describes the world, is actually somewhat larger, right? So you have h squared times s parameter from the state transition. You have s times s h s squared times a from the transition, and you have sa times h from the reward, from the expected reward, and we're not even specifying the distribution of the expected reward, right? So these are like semi-parametric models, and even to describe this semi-parametric model, you need s parameters, and you need these many parameters. On the other hand, like what we want to do is to have a epsilon that's independent independent to s and a, and depend optimally on h. Right. So when in particular when the logging policy and target policy, they are somewhat similar, right? So the on policy evaluation will give us something that can be completely independent to the state action. So we want to generalize that to say if the target policy is a little bit away, and when they are difference is bounded point wise in terms of this importance weight, can we get estimation bounds that depends on the specific choices of polynomial. So it is a statistical estimation problem. It is a somewhat challenging statistical estimation problem when you have many parameters and many parameters need to be somehow averaged out. So you don't need a good model in order to have good evaluation performance. So the second observation that I'm going to be making is that the problem of offline learning, so collecting data that are sampled from a bunch of trajectories, using your exploration policy or logging policy, it is a statistical learning problem. So the problem for optimizing policy and finding what is what the best policy is to solve your MDP using empirical data. So this is a statistical learning problem. In the standard statistical learning problem, what you do is that you find the hypothesis that minimizes, say, the empirical risk. So the number of times that h of x is not equal to y. So y is either, say, cat or dog, and h of x is a classifier that classify any image of an animal into is this a cat or is this a dog, right? It outputs it outputs either cat or dog as well, right? So this is a standard statistical learning problem, and the algorithm that is most common is to solve this so-called empirical risk minimization problem. So on the right-hand side in the objectives, this is what we call the empirical risk that minimizes the observed error. But what we really want to solve, like, is a stochastic optimization problem. We want to minimize the error for new data when xy is drawn from some unknown distribution. So this is a problem that the machine learning tries to solve, and this is a problem this is the best that you can do with your empirically observed data, right? So this is empirical risk minimization. This is a risk minimization, and I argue that the offline reinforcement learning is very similar. Like, it's essentially just a difficult version of the statistical learning problem. So we are still getting IID samples from some distribution. We know a little bit about this distribution, and the distribution is structured because there's an underlying dynamics that's going on. And we also know, say, the exploration policies that were being used. Sometimes we don't need to know the exploration policy. Say, in the previous case, we've seen that using TMIS and we're using the model-based approach, we don't really need to know, like, what the logging policy is, because the estimator doesn't really depend on the logged propensities. I think I forgot to say one thing from the previous observation. So when I was making this comment about the causal inference, I said that there are two cases where causal inference problems are tractable. The first is that you have a model of the world. So this corresponds to the realizable version of the problem. And I forgot to say the second. So the second is when you actually have a randomized experiments, right? When you are doing clinical trials and you are tossing independent coins to decide whether this person is receiving a drug or receiving a placebo. And then, so those are the cases where you can actually estimate without knowing the right model, and with a lot of the missing data, you can accurately evaluate the performance of the drug on this population that you get your patients from, right? So in the RL context, so that corresponds to, say, POMDP, that corresponds to the important sampling-based approach, where you actually know the probability of taking those actions. If you can have that, then you don't need the model. You don't even need the MDP model to be correct in order to have the right evaluation. Okay, yeah, so that was something that I forgot to say. But now let's get back to this slide on the offline learning problem. like how the machine learning problem is dealing with the discrepancy between the risk minimization and the empirical risk minimization is often through something called uniform convergence. So this is about enumerating all possible H within this family of classifiers. So you have 10,000 different classifiers, and then you apply Hofstad's inequality to show that for each and every one of those like classifiers within this family, like this empirical estimate is similar to its population value, right? So which is essentially says that the max over all H in then the ERM. So this is empirical risk minus the actual risk. Absolute value is smaller than epsilon, and then we can make use of this to show that what you learn from the empirical risk minimization algorithm, so by optimizing the performance on your observed data, can actually generalize to future data that you haven't seen. Okay, and it was like even shown that the ERM is the only algorithm that you need to consider, because if a problem is learnable, then it's learnable by empirical risk minimization. So how do we connect this to the offline reinforcement learning problem? So in this case, we want to like find the target policy. We want to learn a policy that's as small as that's as close as possible to the optimal policy, like in terms of its performance difference. So in this case, the empirical risk minimization is simply by maybe coming up with a model, maybe coming up with some OPE estimator, right? And then call that your empirical risk. And then the problem of offline learning becomes simply optimizing by choosing the best policy within the class that maximizes OPE error, right? So that will be the ERM in the offline reinforcement learning problem. Like if we can show that say this is the kind of thing that we have from OPE, right? If we can show that the estimated value for this target policy is similar to its population value, and also if we can show that for this pi hat, this is also smaller than epsilon, then this implies that these two are smaller than 2 times epsilon, right? So there's a but there's a catch. So what is that catch? The issue is that this pi hat is data dependent, right? So all the OPE analysis that we've done so far, like assumes that this pi is fixed, and then we're just evaluating a fixed policy, right? So it's slightly more complicated. So we need to deal with this uniform convergence, where we want to enumerate every single policy and show that with a high probability for the entire family of policies, and like the analogy in the statistical learning case is for the entire family of classifiers, your accuracy on the observed data is similar to the accuracy on the on future data. So in this case, we're saying that for all policy within some specified policy space, then if this is the case, then we can even take this policy to be data dependent. That's not affecting our like argument that get us this 2 epsilon. Okay, yeah, we've already seen like many uniform convergence. So I hope this idea is clear, right? So there are generalization of this of union bounds to beyond the finite hypothesis class, which involve, say, the combinatorial quantities like a VC dimension, like metric entropy. And metric entropy is something that we've learned before. It is a log of covering number. So the metric entropy is just log of covering number, so it's some kind of a dimension. and they're Rademacher complexity type of arguments. So there are entire courses that are dedicated for proving uniform convergence and from the statistical learning theory course. Right. So the main question of interest is what is the natural complexity measure for the typical policy classes in reinforcement learning, and we have some like good understanding of that, at least for the tabular setting and for the linear setting now. Okay, so without making assumptions, there's nothing that we can prove. So let's make some assumption to make the problem easier. So since the goal of offline reinforcement learning is to get the target to find the policy that is close to being optimal, and that is like simply impossible, like without a good exploration. So recall that in the exploration part of the exploration part of the lecture, we have seen examples where like doing uniform, like by taking any actions uniform at random, will result in exponential small probability in hitting those states that actually comes with a reward. Then which means that like in general, like this assumption is non-trivial. But if you are making an assumption that you're running a behavioral policy that visit every state and action pair like sufficiently frequent, right? So at least for those policies that target policies that we care about, then we can define this to be a like smallish numerical value dm. So when this is bounded away from 0, then we can hope to prove something regarding how many trajectories do we need in order to obtain an epsilon optimal policy in offline RL problem. So we'll consider like this will cover today's lecture and the next lecture next Monday. So we'll consider like 3 different policy classes. So this include all possible policies, so this include like everything that we've talked about so far, including the stochastic policies, and sometimes we want to restrict our attention to deterministic policies, and because we know that by the Bellman optimality equation, there always a deterministic policy that is Markovian, that is depends only on the states that's observed, and deterministic that is optimal, right? So we know that the optimal policy is deterministic, therefore we can restrict our attention to consider the family of all deterministic policies. And there's another class called the empirically optimal policy. So these are the family of policies that are nearly optimal from the perspective of the estimated Markov decision process. So these are empirically optimal, means that they are optimal under your estimated m hat rather than m. So pi star may or may not be inside this set of epsilon empirically optimal policy pi hat. And since it depends on m hat, they can be data dependent, right? So these are the 3 policy classes that we'll be considering deriving uniform convergence from, right? So this part of the lecture is based on the work of Ming Ying, who's my student, Yu Bai, who's a research scientist at Salesforce Research, and then myself in the past few years. So we'll start with a family that is the easiest. We'll start with a family with all deterministic policies, right? So for the reason that we know the optimal policies in it, and we can actually like count the number of policies are there in this policy class, and last week we have proven some uniform. We have proven a pointwise convergence bound for the standard OPE problem, OPE with fixed. So let's start here, because then we can use some of the things that we learned before. Okay. So like, how about we start with an exercise, right? So suppose we're given this tabular MDP with S state and A actions and H steps. So this is a tabular finite horizon episodic Markov decision processes. So how many deterministic and memoryless policies are there in total? Anyone? You can type into the chat or unmute yourself and tell me your numbers. This should be straightforward. Anyone? Not a trick question. Okay, I'm seeing some answers in the chat. So a to the power of s and h, excellent. So basically for every like the policy pi decomposes into pi 1 to pi h, and since they are deterministic, you have to choose which action to take at every state and at every time step, right? So at every time state and every time step, you need to choose which action it is. So it is a to the power of sh. So there are so many different deterministic policies, right? So so as we have seen, if you take a union bound, so at the end of the day, it all depends on the logarithmic factor of this. So the error will depend on log of a to the sh, which gives us sh log of a. Right, so that will be the amplification that we get if we take this bound. So now let's try to formalize this argument. Like another issue that we run into is that previously in the last lecture and at the beginning part of today's lecture, we've been working with the mean square error bounds. So these are quantities that are most useful for understanding the performance of an estimator without requiring like unrealistic assumptions, say unboundedness and so on. But it doesn't really give us what we want because if we need to apply the union bound, we need something that's much stronger. We need a result says that with probability of v hat. We need a result that says this is larger than epsilon, is smaller than, for instance, e to the power of n epsilon square. Right? We need something along the lines of such exponential tail in order for us to set epsilon to be 1 over square root of n and maybe log square root of log a to the power of sh over delta, right? So we need something stronger. We need a pointwise bound that has an exponential tail. Okay, so so how do we get that, right? So if we have that, then we can formalize argument and then get a and then get a uniform convergence for the deterministic policy class. Okay, so let's consider how we can do that. So even though previously like we only work on MSE, so maybe some of the ideas are things that we can use to try deriving this this high probability bound. Okay, so what we can do is the following, right? So we can use the same old trick of fictitious estimator technique by first getting rid of the artifacts that's associated with the model-based estimators, which requires a number of state action visits to be somewhat larger, right? So let's define those nice events where the number of visits to this particular pair S and A at time t is larger than like the n times the expected value. N times its expected visiting probability, right? Together with maybe some multiplicative factor that makes it smaller, right? So we've learned in the last lecture that this is something that we can apply the multiplicative Chernoff bound, multiplicative turn-off bound to show that these events holds with high probability. So in this sense that we can like deal with what happens when this event is not true in whatever way that we want, right? So what we decide to do is to construct this fictitious estimator that says that under this high probability event, then I'm outputting the R hat, I'm outputting R hat and P hat that's coming from the model-based estimator. And in those cases when these events fail, then I'm getting the real value from an oracle, right? I'm getting this value from the true MDP and then just plug them in. Okay, so these are estimators that we cannot implement because of these things. Because when this happens, we don't actually have this unknown information. On the other hand, if we can do this, then it simplifies the analysis quite a bit. And all we have to prove, and we have proven that last time, is that like this event holds with high probability. So the differences between the actual estimator and these fictitious estimators, they're identical up to a small probability delta of failure. And that works well with our objective of obtaining the high probability bound, because those are things that we can just put it under the blanket of a small failure probability event through just applying union bound. Okay, so then we can, like for these fictitious estimators, we can construct the fictitious transition probabilities and these transition kernels. We can roll out with this transition kernel to mix the initial distributions for t steps, and at every step, then we'll end up getting the fictitious estimated state visitation probabilities, and the value functions. The value by definition is the probability of visiting each state, and the probability, the immediate reward that you collect at that state by following policy pi, right? So this is the definition of the value, and this is the quantity that we're trying to estimate. Okay, so it is can be shown that the fictitious estimators are unbiased, because it rule out the case when you don't observe anything. So and also, like for the fictitious estimator, we can derive a Bellman equation of variance, which I showed you what it looks like in the last lecture. And in addition, like they come up with a good, like when we do things fictitiously, then they give rise to like easier derivation of some like a decomposition of terms, basically still based on the Bellman equation, but then we can parallelize everything, and then that gives us a good martingale decomposition that we can make use of. Okay, then and the last thing is what I said just now. So when we assume that the state action visitations is under mu, so dm is a lower bound of the d under mu s a t for any s a t, right? So it is a lower bound of that. Therefore, like under mild conditions, as long as the number of trajectories is this large, right? So it's not restrictive at all. So as long as we have a constant number of trajectories, if we assume dm is a constant, then the probability of the fictitious estimator being the same as the true estimator happens with probability 1 minus delta. And what's what more that we can observe is that we can actually add this supremum in front without losing anything. So why is that the case? Because this probability has nothing to do with the policy pi, right? So this probability, like the randomness, are completely due to your logging policy and due to the random coins of the environments. And no matter like which pi that you choose, Like it doesn't change anything. So provided that you have visited each and each individual SA pairs, um, as long as you visit each individual SA pair sufficiently, like more than once, like as long as you visit every pair of state action at every time point at least once, then your V tutor is identical to V hat, and this holds for no matter which pi that you plug in. Okay, so one problem solved, and then what we can do is that, so this reduces the problem of solving the pointwise convergence problem of V hat into solving the pointwise convergence problem of V tutor. Okay, since by triangular inequality, right? So sup pi V hat minus V is smaller than sup pi V hat minus V tilde pi plus sup pi V tilde pi minus V pi, right? The first is 0 with high probability, so it remains to deal with the second, right? So when we deal with the second, what we can do is to apply the definition of this V tilde. So we can decompose this by the estimated model into these. So these are by the definition of V, and then we can like do the triangular inequality thing again by adding or removing things. So we can decompose the error into two parts. One of the parts we only need to deal with the errors in the reward estimation, and in the other part we only have to deal with the error that's due to the estimate of the state visitation measure, right? So the second part, so this part deals with only the reward, right? So this follows from triangular inequality, and so this requires R tilde to be similar to RT, R tilde T to be, and this part, so as long as we can show that the D tilde T is similar to DT, then we're done. The second part is much easier, which we can see how it we can see how it works right away. So basically, observe that these R tilde T is completely like whenever we condition on the number of points that we observe, right? These quantities and these estimates are independent to the choice of a pi that we choose. So we can apply Holder's inequality, right? So we can apply Holder's inequality and then bound this with L1 norm and R tilde T minus RT with L infinity norm. Right, and just now from the previous lemma, we know that with high probability, the number of observations NSA is larger than, so under the event, right, under the high probability event, this is larger than dn times dm and times half, right? So with high probability, this holds. And in fact, and when this event is not hold, and since this is fictitious estimator, you actually get 0, right? So R tilde of T minus RT, so this is the same as under E plus R tilde T minus RT indicator E complement. So under E complement, this is 0. So it remains to deal with a case that happens under E. And when this event happens, we know that the state and actions are visited sufficiently many times, then we can apply Hofding's inequality. Yeah, you've also worked this out in the homework 1. Remember, so I asked you to deal with estimation of the reward, right? So you can enumerate all the state action pairs, and in addition, in this case, we enumerate over all T, and you can show that R tilde T S A minus R T of S and A, this is smaller than NDM and log HSA over delta with probability 1 over delta. This for all SAT simultaneously, right? By Hofding's and union bound, you can prove that the reward part of this is okay. Yeah, I started a little bit late today, so I'll take like I guess 2 more minutes, so I can cover what I wanted to cover. Yeah, I'll do that briefly. So it remains to bound these terms, right? So it remains to bound this more difficult term that deal with this d theta. So what we can do is to write it in a slightly easier way that allows us to apply concentration, right? So first of all, like this is so we can derive a dual representation. So this in the primal representation of the value. So this is a marginal the marginal distribution or the occupancy measure representation. On the other hand, we can rewrite these differences to be simply based on the value function, right? We can actually decompose this into the value function multiply with the error in the that you got in the first step, and then later, so we are getting the error that's inherited from the previous step together with our estimated transition kernel. So this T denotes the transition kernel. So it's just a matrix version of that transition dynamics P matrix. So we'll see how this works. So so basically we can write down the transition equation of these. So these two grouped together gives you this transition P tilde on the pi, and these two gives you the transition P in pi. So this is our S by S. These two together is our S by S, right? And this is our S by SA, and pi t takes this A and then sum over the A, right? So these are just some matrix notations, but like you should just think about this as a matrix vector multiplication, and that's the easiest way to think about it. And then once we have this, we can just take the difference of these two Markovian transition, and then that like then we can add or remove things to decompose this error into two different terms, right? So decompose the error of d tilde into two different terms, and then we can recursively apply this and think about this matrix. This is something that you worked out in homework 1. So this is a transition matrix. This is a multi-step transition matrix that got pulled together. So this is a probability that you transition from S to S prime like H steps after applying this target policy pi. Right. So these together with the transition of the current steps, these come directly by recursively applying this, by substituting the same formula into that, and then substituting the same formula further into the next into the next D again and again and again, and then you will get this recursive expression that decomposes the error into two terms. So this term is coming from the error of estimating the first state distribution, the initial state distribution, and everything in the middle. So these are coming from the error in estimating the transition probabilities. Okay, so once we have that, we can we can add another level of summation. So notice that this is only like dt tilde minus dt, and what we want is this inner product with what we want is this inner product with RT, right? So what we can do is to plug in this into this expression and call this expression X, and then we can just work out the algebra, and that decomposes the error into the summation of two groups of things, and what we end up getting is something that's nice because it gives back the the value functions. So in every iteration, so we have these true value functions that's not a function of the data, and the true value functions of here that's counting from V1 to VH. And the randomness and the data dependent quantities on the other side of this inner product, which also decomposes according to the individual estimation problem of the individual parameters of the MDP. So initial state error and the error of your transition kernel based on your empirical observations. And I further argue that this decomposes the error into a martingale, into a martingale, and the reason is the following, right? So since this is the summation over H, so at time H, so everything here, right, only depends on things that happened in the past, right? Past in terms of the steps of this Markov decision processes, and yeah. So yeah, let's talk about this in the next lecture. So I wanted to be to make sure that we understand how we are constructing this martingale and how we can show this is martingale and then apply the concentration. So I'm already way over time. So let's stop here. I'll see you guys on Monday.